Alrighty, so let's continue with our exploration of the wonderful and mighty features of Python and Jupyter Lab. Or we could talk fluid mechanics, it's your choice, but I'm guessing since you're not in that class yet, we can get rid of that. I bet the server's not running right now. It's not. Pictures up to date. And as we usually do, don't want that one. Yeah, right. Let's get another instance up and running so that we can do examples. And our favorite notebook name, Untitled 1. Not to be confused with Untitled or Untitled 2 or so on. And let's get to this class. I know what the topic for today is. It is data structures, but I guess I need to get to the class. This is you guys. Notes. Structures. So we're now moving from variables that have a name and just get one thing stuffed into them into variables that have a name and can get a bunch of things stuck into them. So that comes under the generalized heading of data structures. We'll explore what data structures are. Then we'll explore three of the ones that you'll encounter at some point: lists, tuples, and dictionaries. And near the end of this morning, I'll at least mention arrays. When you learn NumPy in a couple of class sections, you'll completely forget that there's a whole array package, because NumPy manages aspects of that for us quite effectively. Also, in this particular presentation, we'll introduce some utility of conditional statements. We actually have visited selection already, but it'll start to take on a more important role. So first, what is a data structure? Deep breath. Data structures are specialized means of organizing and storing data in computers in such a way that we can perform operations on the stored data more efficiently. So as definitions go, we'll practice some selection here. That is A, a useful definition, or B, absolutely useless. That's a useless definition. That doesn't tell me anything. But data structures are ways of organizing collections of data. So the four main structures we'll look at today, one is called lists. Second is called a tuple. Silly name, I don't know where it comes from, but tuples have some special properties. A third is called sets, and a fourth is called dictionaries. Sets and dictionaries look an awful lot like each other, but they are not identical. There should be another one over here called arrays, but it was told to me by the development team for the class that to use arrays you have to load in the array package, so it's not a primitive data structure. Fine, all I did was white it out in the graphic. A reasonable mental model for a data structure, one that works for me, and I'm definitely mental, is it's a variable that has a name, but inside that variable it's got multiple parts. An example we've already seen is a string. A string has a name, and inside the string we have multiple characters. I mean, if the string is something other than character A. And remember how we accessed say the third character of a string. Let's say the string's name is string, and we want to access the third character of the string, assuming it has at least 3 characters. Does anyone recall how to do that? Square bracket with the number 2. That's correct. And why did he choose the number 2, other than to get the correct answer? Because that's, you get extra bonus points for being right. It's because we start counting at 0. So the first element of the string is element position indicator 0. The second element of the string is position indicator 1. The third one is position indicator 2. That's an example of a variable that has a single name, the string name, and multiple pieces to it. So we can extend that idea to other data types. So the first is a list. A list is just a collection of data that are somehow related. It's a convenient way to refer to a collection of similar things by a single name and then using an index, just like a subscript in math, to identify a particular item. So if you were to consider the math-like variable x, assuming they still do subscripted variables in math class, and I can't imagine they wouldn't because they've been doing it for 300 years, why stop now? We could have x sub 0 has a value 7, x sub 1 has a value 11, x2 5, x3 9, x4 13, all the way up to whatever xn is. So the n is how many things are, 2, 2, 3. So the variable name is x, and the subscripts correspond to different values of the variable. So, for example, the value of the variable named x associated with subscript 3 is the number 9. And so here's a visualization of that. Let's suppose we have a variable named myList, and in myList we have cells that represent where things go in that variable. We'll use Python-like counting, so we'll start at 0 and work our way up. Cell 0 takes on the 7, cell 1 takes on the 11, and so forth. The contents of a particular cell is its value. The index is whatever the cell address is, and the variable name is the variable name. So if we wanted to refer to the value 13, that would be myList square bracket 4. And if we somehow interrogated myList, we would get a 13 back. That's assuming the list is numeric. If it's a string, we would get whatever that string is, and so forth. Lists are actually simultaneously both very powerful and very easy to confuse stuff with, because a list doesn't have to all be numeric. A list can contain other lists, so we can have lists of lists. Lists can contain dictionaries and tuples, so we can have lists of dictionaries, lists of tuples, and so forth. But the take-home message on the list is it's a way to refer to a bunch of things by a single name. And there will be times when that's useful. So in engineering and that respect data science, lists get used a lot. Sometimes we call them vectors, matrices, arrays, tensors, but ultimately, at least computationally, they're just lists. To declare a list, you simply write the name of the list and assign it values. The square brackets are what are used to identify that the variable is a list. So for example, there's my list, and I'm not going to type, but I will drop it into our untitled thing. I'll put it right there. And I will actually see, how do I nuke everything else? Let me go ahead and do my little clippers out. Bye-bye all that good stuff. Okay, so there's my list. And if I execute the cell, I see nothing back unless I... And so what it's going to do is it's going to render the contents of my list back to my notebook. And more than just rendering back to the notebooks, subtly it's actually told us that it's a list. We learned that because it's being printed back with square brackets and the individual elements are separated by a comma. And now if we want to find a particular element, so somebody choose a number between, I think, 2, 3, 4, 0 and 7. 7 it is. Oh, let's put it in the right place so it works. And we get the last element back. If you had chosen a different number, we'd get a different piece of the list back. We can create another list, which, because of my lack of naming creativity, is called my other list. And notice that it has square brackets with nothing between them. That's called a null or an empty list, and that is useful for creating storage space for other operations. So there's my other list, and let's go ahead and so the first statement will create my other list. It'll be empty. The second statement will attempt to render the contents of my other list. I think it'll report back an empty list. It might use the word null, but I'm not sure. It tells us that we have an empty list. So if we want to put something into the empty list, speculate how you might do that. Any ideas? Let's say we want to put the number 32 into my other list at position 0. Okay, since none of you are playing along, one way we might try is to do my other list. We want to assign something to position 0. And what did I say, 32? And so at first glance, that seems like that might work. How are we going to know if it's going to work? Go ahead and attempt to execute it and see what happens. And it says, list assignment index out of range. And it's like, how can that be? That makes complete sense to me. The reason is when we're adding to an empty list, we have to use something called the append. See if I have the order. I think I have the syntax correct. So we're going to attempt to append to my other list the value 32. And it didn't like that either. And that's because I'm not doing it right. Yay! Took me a while. But like you, I'm persistent. And I always could have gone off to the internet and copied. Now let's look at the contents of my other list. It should have one element in it, and the value of that element is 32. Sure enough. What if we want to add an additional value? Somebody choose a number between 0 and 100. 14 it is, which is half of 28 for those of you at home without a calculator. So if I execute that cell again, which I can do, that's easy enough, what do you think is contained in my list? First question, how many things do you think are in my list? 2 or 3? Okay, we'll print it out. I think it's 3. The reason being is I never cleared the list when I did the append again. So append you have to be careful with. But we'll find that out in a second. And so when I display my other list again, sure enough it has 3 things. We can defeat that by using something that I probably shouldn't show you, but we will see. That reset force. And now it gives us an error message. What could I have possibly done wrong there? This particular function is called a Jupyter magic function, and that wipes everything in the memory associated with this notebook, including the existence of my other list. So now that I have wiped everything, let's go ahead and recreate the list, append to it, and now when we look at it, we'll only have two things. Okay, so that was enough silliness. Let's continue. So Python indices, we already know, start at 0, and the first element has an index 0, 1, and so on. Our first type of special list is something called an array. And the primary difference between an array and a list is, by definition, an array is a list that contains elements of one data type. So we can have arrays that are comprised of floats, arrays that are comprised of integers. I think we can have arrays that are, they're numeric. Arrays have the property that they're ordered, which means the elements can be indexed, and they have the property that they're mutable, which means we can change the contents of an array. That'll come in, that distinction will come in shortly when we talk about tuples. When we create an array, we have to tell it if it's going to be a floating point, double precision, which is a special type of floating point. It's twice as good as regular floats. Lowercase I for assigned integer, uppercase I for unsigned integers, and each of those data types has certain utilities in practical applications. And there's a lot of other choices, and the table that I'm scrolling through somewhat slowly has the different types of contents that can go in an array. And this last column describes the smallest size of each element. So for example, a signed character is treated as a type integer. The smallest it'll be is 1 byte. A floating point, the smallest it'll be is 4 bytes. Double precision, smallest is 8. Yes? Pardon? Yes, you can. To use arrays, we would use the array library, and we'll just cut and paste and go look at that quickly. When we get to NumPy, you will immediately forget that there is such a thing as an array, because the NumPy lets us manage them a little different. So have we done imports before? We have not, I don't think. We did it in lab, but it was just presented, just do this and continue. So what we're doing here is all the stuff to manipulate arrays is stored in some other file that's not part of our current Python kernel. But it is part of the current Python install. To use it, we have to import it. And so all that did was import a whole bunch of code that I never see. As a user, I don't actually care about it, other than it works. As we go to more advanced stuff, I think the one we already did was we imported the math library so that you could do stuff like sines, cosines, and square roots. They created that structure so that they could keep the load sizes of various Python installs small. So you don't import functionality unless you need it. That's the thinking. It is opposite of anything Microsoft does, which is to put everything in it, make it hacker enabled, and then you have to disable it. The Python mindset is we make it as small as possible, and then you add to it as you need stuff. It's just a different way of thinking. End result is the same. We're going to make numbers come to life and then go away. I keep clicking to the wrong thing. So now we're going to create an array. We'll call it my array because, again, I have no naming sense. So my array is the name of the array, and we're using the array package, so we have to prefix every function that's part of the array package with the name of the package. In this case, it's array. So we have array.array, which is admittedly a weird-looking statement. And the first parameter we're passing to the array.array function is lowercase I as a string. So we're telling it it's a type of integer. And then we're now passing a list to that array, and that list will take on the properties of an array. So if I print it back to myself, it just kind of regurgitates the command. If we see what type my array is, it tells us it's an array. And sometimes we don't like long words, and so notice how I changed the import command. That's called aliasing. And so I'm associating the characters AR with the package array, and it allows us to make sure I do this correct. Yes. It allows us just a different way to access packages. You'll see that NumPy, when you steal it off the internet, copy, cite, modify, run off the internet, is normally import NumPy as NP, and then everything else is NP dot, whatever the various functions are. We'll see pandas, import pandas as PD, and then it'll be PD dot, whatever the functions are. And that's a fairly common approach that's taken with Python stuff. And you are encouraged to go to the internet and borrow other people's stuff. Here I'm importing it as ARR. And we can get the first element of my array. By accessing it that way. Let's see what type of variable the first element is. Because I really don't know. It is an integer. And why is it an integer? Because when we created the array, we used the integer code and said that everything in this array will be an integer. So how would we add an element to the array? Any ideas? This is your short-term memory test. Append. And what do you want to append to it?
64.
Oh, we have a terrible result there. I must have made a mistake. I typed extra garbage there. So we've appended 64. And now how will we get how long the array is? We introduced the length function a couple of labs ago. Okay, how long do I think it is? So 1, 2, 4, 8. So it started out as being 6 elements long. We appended an element, 64. Oh, I see why you chose that number, by the way. So we should get a result of a length of 7. Now length is it's counting things. It's not indexing things. There are 7 things in our array. 64 is at what position in the array? It's what you're thinking. It's at position 6. The first position is 0. Oh, the length of the contents of the array. If we type the array, we just get the object back. But if we ask it what the length is, it's the count of the things in the object. And moving on. Lists can store elements of different kinds of data. Arrays store only one kind of data, whatever you create it as. Arrays are lists, but lists are not quite arrays. Our next one is a tuple, which is a special kind of list. And I'll read this to you. A tuple is a special kind of list where values cannot be changed after the list is created. That sort of sounds stupid, but it has some utility. Such a property is called immutable. So that's a fancy word for you can't change it. They could have called the property the you can't change it property, but they looked up a word in the dictionary and they found, oh, this immutable word, that's a weird looking word. That way we'll have job security, so we'll use immutable for that. It's useful for lists like things that have to stay static, like days of a week, months of a year. And you declare a tuple just like a list, except you use I call them round brackets. I guess they're parentheses actually. No, round brackets will work. So that's the first visual appearance of the difference between a list and a tuple. Lists, square brackets; tuples, round brackets. This is probably the most important statement today. That won't make much sense now, but later on it will be valuable. Tuples are often what are created as outputs from packages and functions. So we run some function, we download it off the internet, produces output, and we can't access the output because we don't know that it's a tuple. That's what the type function tells us. It'll tell you it's a tuple, and knowing that, all of a sudden you can write the rest of your script to use parts of a function. Other than that, we're not going to dwell on tuples very much in this class. Keep that somewhere in the back of your mind. Keep it in the readily accessible part of your mind for the next 4 months, and then in the back of your mind for time beyond that. Removing individual tuple elements is not possible. There's nothing wrong with putting together another tuple with the undesired elements discarded. To explicitly remove an entire tuple, we use the delete statement. So tuples can be created either by ourselves explicitly or by functions or packages that we've installed. And tuples can be destroyed. Tuples can be accessed. We can look at the contents of a tuple, but we can't change it. If we want to change the contents of a tuple, the easiest way is to create a new tuple and pull from the old tuple the stuff we want to keep and then toss the stuff we don't want to keep. So here's an example. We have a tuple called a tuple, and it's going to be comprised of 2 characters, the character A and the character B. As tuples go, that's a pretty dumb tuple, although it's only got 2 things in it, so 2 tuples. And then if we print the contents of a tuple, we get A and B back. Big deal. Now let's suppose we want to add a value C. To create that, we take our new tuple, we call it added value tuple, and we put in the value of the added value, which will be the C. You see a comma, and you notice that it's a dangling comma. So there's space left after the comma, and so we can make a short tuple, which is the element number 1 of a tuple, which corresponds to the letter B, also a dangling comma. And the new tuple, we can just concatenate the short tuple with the added tuple value. We'll delete the original tuple, and then we'll print the new tuple. That's the only thing that's left, and we get a B and a C back. That is a monumental pain in the ass to do what we just accomplished, but that is a, we can call it a feature. That's the consequence of immutability of a tuple. So notice at no point there did we actually change the contents of a tuple once it was created. But creating tuples and pulling pieces out of tuples isn't all that hard. So we have another special list called a dictionary. And this is a list where the items are related data in pairs. It's It's a lot like a relational database, and in fact, I think it actually is one, and we won't learn about relational databases for a few days yet. The first term in the data pair is called the key, and the second term is the data. The second term itself can be a list, and that can be a list that contains other dictionaries. So dictionaries can get quite nested and complicated. In the lab, you're going to have some unnecessarily complicated exercises messing with dictionaries. It's just to get you in the right mindset of keys and data. So we can declare a dictionary using curly brackets, and we'll go through that in a second. Or we can use the dictionary method, which is built into Python, which is keyword dict, D-I-C-T, and they're almost the same, but there are some syntactical differences. They're fairly minor, but if you mix the two, you just get an error message. So we'll do the first one, my pet's name and mass, and open curly bracket. And so the first thing in quotes is the key. So in this case, I have a key named Dusty, and it has a value of 7.8. Next, the comma, and then the next item is the key named Aspen, and in a value of 6.3. The last one is a key named Marry Me, and a value of 0.03. Or we can create the same thing using the DICT method. In that case, you take the key, you don't have to put the quotes around it anymore. We're just naming it. We're saying Dusty is equal to 7.8, Aspen is equal to 6.3, Marry Me is equal to 0.03. Those two dictionaries, although they have different names, their contents are identical by design. We did that on purpose. And let me do it right here because it's already done. So if we execute those two statements and then print back the contents of the dictionary, my pet's names and mass, my pet's names and mass 2, we see that the two dictionaries are identical. Dictionaries are useful where you actually want to associate data with keys. So instead of addressing them by list name, index, you can address it by dictionary name and key. Another kind of special list is called a set, and they're used to store elements of different types of data. Sets are unordered, mutable, and they do have the requirement that there's no repetition of elements in a set. Sets are also enclosed in curly brackets. So here's the first major screw-up of structures that is embedded into the Python language, and it's going to be there indefinitely. So here we have a set in curly brackets, and so that first element is using numbers, and they kind of play the same role as a key. And so we'll call that my set, and we can get from values of my set by the key the various elements. So element 3, the third key of my set, is this additional set that contains 1, 2, and 7 of 9 as the data elements. So if we take my set, we use the get function. It says get the third key from my set. So it goes 1, 2, 3. There's the third key. And so the item in the third key happens to be another set. And so now when we execute the get on that other set, it's going to get go to the third key of that, and it'll return the data, which in this case is 7 of 9. Another way to create sets is without explicitly creating keys. And again, we can make a set 1, 2 is 77. It has type set, and we can access it with the get method by just simply specifying the item out of the set that we want, the third item, the fourth item. But keep in mind, sets aren't necessarily ordered. So 177.2 and 1-2-77. Logically, they're the same set, but using the get method, you might not necessarily return the same thing. Here's another example of a set called your set. So it has apple, cat, rock, the number 77, sunset strip, and if we type the contents of, if we interrogate what kind of object your set is, it tells us it's a set. But once we have sets, we can do some cool set theory kind of stuff. We can join and intersect sets. So the union operation is indicated using the vertical line, which is the pipe symbol on your keyboard. So if we print the union of my set and your set, it takes the elements of my set and the elements of your set that are not common to each set and creates a new set. So the union is the new set 1, 2, rock, 77, cat, sunset strip, apple. And I would have to read again how it actually orders them. And the intersection, so the only thing my set and your set have in common is the 77. The intersection is, it returns 77. So you can think of it, this is the computational construct of Venn diagrams. They still do that in math class, right? Venn diagrams, circles, and you have the overlaps, and you do them in pretty colors. And then it's time to eat the kindergarten paste and take a nap. There's another way of constructing a set called the set constructor method, which if I don't press the keys wrong, we'll be able to look at. So we have a set that we've named this set, and the keyword is the word set, and it's double round brackets. And so now we're creating a set that contains an apple, a banana, and cherry. And if we print the contents of this set, it just gives back a set, apple, bananas, cherry. The obvious question is, what's the difference between a set and a dictionary? Because they both use curly brackets. I'll read the first one. A set is like a dictionary where the keys themselves are the values. That's probably the most useful mental model of what a set is as compared to a dictionary. The other one that I really like, because this is a useless explanation, and you got to get very comfortable with useless explanations. The internet is full of them. Well, a set's like a dictionary with keys but no values, and they're both implemented using a hash table. So now they just went geek on us in trying to explain what the difference is. But yes, it's annoying that the curly bracket notation denotes an empty dictionary rather than an empty set, but that's a historical artifact. So that is a useless comparison. So as you're doing your own research to try to figure out what the heck we're asking on our homework assignments and labs, bear in mind you have the obligation to try to decide if what you've internet searched is useful to you or not. So what's in blue right there is not wrong, it's just not very useful. In our example below, we can look at empty versions of each. We can create an empty dictionary. So I'm going to create a dictionary named Webster, and if I type Webster, if I print what type of object Webster is, it comes back as a dictionary. If I create an empty set using the set constructor with nothing in it, and then type that object, it comes back as a set. And then once they're created, there would be a reason to have an empty dictionary or empty set. We can add stuff to sets, but I don't think we can't add them to dictionaries. So let's summarize, and then we'll send you all off to lab. So dictionaries, not ordered. The elements in a dictionary cannot be something. They're changeable, but the keys are not. So the key in a dictionary are not alterable. The data associated with a key is. So a dictionary is like a database. That's how I think of it. Tuples are, I don't have a bullet list for tuples. Lists are ordered. They're indexed. Lists are changeable. You can change the contents of a list, and we can apply operations to each element of a list. And you'll get to do that in lab. So I'm going to cut you loose in about less than a minute. Let's go see what the first lab is. I want to be sure. Yeah, you're going to be playing all these examples in lab. So I will see you in lab in 10 minutes. Thank you for your attention, patience. Hopefully everybody's awake now. You had 48 minutes to thaw from getting here. And I need to turn off the recorder before I mess up.